In this video, we're going to look at polar equations and their graphs. And for some of you, this may be a review. For some of you, this may be new. I'm going to kind of go through these ideas as if they are new for you. You can see here, this is our polar grid. And you can see on there the XY axis that we're used to from the rectangular grid, but instead of having rectangular grid lines, they are now circular. And if you can imagine our unit circle, those angles, those are what are represented by these spokes here. So for example, of course, this would be 0. Here at the top, pi over 2. This would be pi. 3 pi over 2, and this spoke would even be 2 pi as we make our way all the way around. I'm not going to label every spoke, but I will get these here in the middle. That would be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so hopefully you can kind of see those spokes. Think about your angles from the unit circle. The pi over 6, pi over 3, pi over 4 angles all the way around the circle. Now, in rectangular Cartesian graphing, we are used to points being designated by an XY coordinate. In polar graphing, the coordinates of a point are r theta. And obviously, theta is going to stand for the angle. R is a radius because this is a circular way of graphing. The R is a radius. So let's say I've got point A here that has the coordinates 4, 5 pi over 3. So if we're going to plot this point on our polar grid, I'm going to go around and find 5 pi over 3, which would be this spoke right here. 5 pi over 3 is over in quadrant 4. It's that pi over 3 angle there. And then the 4 is the radius of the circle. And so I'm going to count out from what I will sometimes call the origin, but really should be called the pole when we're doing polar graphing. This is the pole. And I'm going to count out a radius of 4, 1, 2, 3, 4. And so that would be point A. Let's try another one. Point B, 3, 7 pi over 6. If you want to, pause the video and try to graph that, plot that point yourself. 7 pi over 6 is the pi over 6 angle over here in quadrant 3. My radius is 3, 1, 2, 3. That point would be, point B would be B. I'm saying B a lot. It would be right here. Now, I did not point out on the spokes earlier. You'll notice that there's more angles marked with these spokes here than what we're used to on the unit circle. They're actually marked every pi over 12. So this would be pi over 12. This would be 2 pi over 12, which is pi over 6, 3 pi over 12, which is pi over 4, and so on, all the way around. So those spokes that are closest to the x-axis and closest to the y-axis, those we're not used to seeing on our unit circle. They're extra angles. Let me give you one more point. Well, actually, I'm going to do more than that, but let's do one more to try to graph. Notice this time I've given us a negative radius, -2, and our theta is 5 pi over 4. When we have a negative radius, we're going to find our spoke, 5 pi over 4, which is of course, here in the third quadrant. But if my radius is negative, that means that it's going to send that point on the same spoke into the opposite quadrant. So we're going to go over to the first quadrant and plot the point here at a radius of 2. This is point C. Now with that point, now being over here in the first quadrant, you might be thinking, oh, well, we could have written some different coordinates that would represent that same point. If I used a positive radius of 2, then my theta would be pi over 4. And so this is a feature that's a little bit different in polar graphing, is that when we have a point on the polar grid, there are multiple ways to write coordinates that represent the same point. And that's something that just doesn't happen in the graphing, Cartesian rectangular graphing that we're used to. Okay, now you can see I've added 2 points to our graph here over in quadrant 2. And I want you to pause the video and in just a moment and write at least 2 sets of coordinates for each of those points. Now you can see here for point D, I'm guessing that most of you probably wrote these first 2 types of coordinates that I wrote for point D. You'll notice in the next 2 sets of coordinates that I wrote, I introduced negative angles. I could use a negative 4 pi over 3 angle, which of course would start here and go around in this direction to here. That would be negative 4 pi over 3, and then my radius would be positive. Or the most complicated of the 4 is to do a negative radius and a negative angle. So negative pi over 3 and then negative 5 to get up to D. And then for E, I did something similar. All 4 of these coordinates would be representative for point E. So that was just a brief introduction to how the grid works. I want us to, one of the things that we're going to need to understand is how these polar graphs relate to the rectangular graphs that we are more accustomed to. How is r theta related to xy? Well, I'm going to plot a point here and draw for us a reference triangle. Maybe you remember this from pre-cal reference triangles when we were first learning trigonometry. The sides of this triangle, the horizontal side down here would have length of whatever the x coordinate is. The vertical side would have the length of whatever the y coordinate of that point would be. Think about this point on an xy plane. And then in polar, the hypotenuse of the triangle has the length of r. And then the theta, of course, is the angle that's represented down here. And so just using this triangle, the cosine of theta is going to be the adjacent side over the hypotenuse, x over r. And if I solve this for x is equal to r cosine theta. This is going to be one of our conversion formulas. The x coordinate from rectangular is equal to the radius times the cosine of the angle. And similarly, sine theta is going to be the opposite side, y, over the hypotenuse r. And if I solve that for y, y is equal to r sine theta. And so these are going to be the conversion formulas that we can use to think about the relationships between polar and rectangular. And for us in calculus, the important thing is going to be when we want to find the slope of a line tangent to a curve. Slope is still going to be in terms of y and x. It's still going to be a dy dx value for us. So that was just a brief introduction into kind of how the polar graph works. There's more to the pre-cal aspects of polar that I'm just not going to take time to go into in this video because I really want to get into how to sketch the graphs of the polar curves. That's one thing that we kind of need to be comfortable with in calculus is how the polar graphing of a curve works so that we can understand how to apply the concepts of calculus to it. So if you have picked up a packet, in there's a sheet of some common polar curves, and we're just going to look at some of these just to have an idea of what happens. In these first curves up here, you can see these are just circles. Let me start with this one. We've got a circle here centered on the x-axis. The equation for the circle is r is equal to a cosine theta, where a is greater than 0. And in this case, for this particular circle, the a would be 3. 3 cosine theta would be the equation of this graph. That's going to give us a circle. If a was negative, like negative 3 cosine theta, then it ends up centered on the x-axis but on the left side. If r is equal to 3 sine theta, we still get a circle, but centered on the y-axis, and negative 3 sine theta would be centered on the negative y-axis. These next graphs here, cardioids, limacons, these are the ones that we're going to learn how to graph today, and you can see the equation looks a little bit different. It's not just a constant times the trig function, but we're adding or subtracting a constant here in front. I should have said a coefficient with the trig function, and then we're adding or subtracting a constant in the front. And depending on how those two numbers are related, the a and the b, we end up with a graph that looks like this, or sometimes we end up with a graph that has this inner loop. And that's one of the things we're going to explore, is why does that inner loop happen? Now, if you did have some experience with polar graphing, I'm sure you remember these flower curves. They're always a lot of fun to see, and we are also going to learn how to graph, how to sketch those graphs as well. So in your packet, you should have some grid paper that has polar grids on it, and then also has an XY axis located down below. These are the ones we're going to use to sketch our polar graphs. And we're going to start with, let's start with the polar equation r equals 3 plus 3 cosine theta. R equals 3 plus 3 cosine theta. Now, when you first learn polar graphing, typically an approach to doing this is to make a long table of values, pick all these special angles, find out what they're equal to, plot the points, and then connect them all to make the curve. It's effective but tedious. I like to take a different approach. We're going to take this equation, and we're going to graph it down here as if this is the theta axis and this is the r axis, and we're going to graph it kind of in a Cartesian way. R is equal to 3 plus 3 cosine theta. So if you think about how to graph trig functions, another part of pre-cal review here, this first 3, that's going to be the midline of our graph. It's a vertical shift of that parent function for cosine. So I'm going to go up here to 3. That's going to be the midline. And then this 3 in front of the cosine, that represents the amplitude of the graph. And so from 3, I'm going to go up. This graph is going to go as high as 6, and it's going to go as low as 0. That'll be the bottom of the graph. And I should have labeled my theta axis pi over 2 pi. I'm just labeling the axis angles. Okay. And we really want to think about all of these curves like one quadrant at a time. So 3 cosine theta, if it's cosine, cosine starts at the top of the cycle. So it's going to start up here. It's going to go to the middle, bottom out, back to the middle, back to the top. That's what our cosine graph looks like. So instead of making a table of values, we're going to use this graph to just kind of in our head think about what the coordinates of these different points are. And as I sketch this graph, I'm going to use a different color for each quadrant so we can kind of make connections maybe a little bit better if you like color. I love color. So I'm starting here, quadrant 1, 0 to pi over 2. My curve starts up here at 6. So when theta is 0, my radius is 6. So that point is going to be out here right there. This darker line here represents 5. That's a radius of 5, and so I'm just going 1 past that. When I get to a theta of pi over 2, my radius is 3. So on pi over 2, I'm going to be here at 3. Okay, so we have those 2 points. You're like, okay, well, how do we connect them? It's going to be, a curve in nature. This is a polar graph. We should be expecting something curvy, but it is very helpful to have a third point to kind of help us make the curve. And what I like to do to get that third point is to think about the function that we have here, cosine theta. which angle is going to have a really convenient value of cosine theta? Well, that's of course going to be pi over 3 because cosine of pi over 3 is 1/2. And so if I do r of pi over 3, that's going to be 3 plus 3 times 1/2, which would be, 3 times 1 of 4.5, 4.5. So at pi over 3, I'm going to go out to 4.5. Sorry, I'll write that up there, 4.5. That gives me that point right there. And so now, and this is scary, I usually do this with a pencil, but I'm doing it with a marker. Okay. So our curve is going to look something like that. Curved in nature, connecting those 3 points. And that connects to this part of our graph down here, right here. All right, I'm going to switch over to another color for the next quadrant. So for quadrant 3, pi over 2, of course, we're picking up where we left off here at this point. And when I get to pi, my curve here is at 0. I have a radius of 0. And so what that means up here is that when I'm at pi, my radius is 0. My point is just here at the pole. And so if you think about that, anytime we have a radius of 0, regardless of what the theta value is, regardless of what the angle is, that point is going to be at the pole. So now how do I connect this point to that point? We're going to have a little curve over here. So let's find that third helpful point, which is going to be at the 2 pi over 3. If I do r of 2 pi over 3, that's going to be 3 plus 3 times negative 1/2, because cosine of 2 pi over 3 is negative 1/2. And so now I'm getting 1.5. So on the 2.3 spoke, we are here at 1.5. That is our third helpful point. And so the curve is going to go like this. And again, that corresponds to this, this piece of the graph down here. So notice down here, as this part of the graph is very close to the x-axis, this part of the graph up here is getting closer to the pole. And in fact, when this graph touches the x-axis, this graph, the polar graph, touches the pole. Let's move on to quadrant 3. Of course, we're going to pick up where we left off, and it's going to go out to 3 on the 3 pi over 2 spoke. So 3 pi over 2, 1, 2, 3. And notice down here, we of course have symmetry. It's one thing I love about trig graphs is all the symmetry that's there. Same thing's going to be true in their polar counterparts, that it's going to be symmetric here in quadrant 3 to quadrant 2, just like it is down here on this graph. So this 1.5 point that we found at 2 pi over 3, we're going to have that same point at 4 pi over 3. And the graph is going to connect like that. And then for our last quadrant, of course, we're going to pick up where we left off. It's going to end when the theta is 2 pi. We're back at 6. 2 pi 6. That's that same point where we started, which should make sense. A cosine graph always ends where it begins. And this quadrant is going to be symmetrical to the first one because that's where these pieces of the graph are the same. This graph down here is going to mimic what we graphed up here in quadrant 1. So on the pi over 3 spoke, the 5 pi over 3, we're going to have that 4.5 point. And then we're going to connect like this. And so there we have our first polar graph of a cardioid. Okay, for our next example, we're going to graph r equals 2 plus 4 sine theta. So in that first example that I did, remember that the constant and the coefficient, they were both 3. They were the same. In this example, our constant and coefficient are different. We're going to see how that affects our graph. We're going to take the same approach by graphing it down here using this, the vertical axis as an r-axis, the horizontal axis as a theta axis. I'll just rewrite our equation down here, 2 plus 4 sine theta. So this constant, that's going to become my midline. That's a vertical shift of the parent function. So my midline at 0 is going to move up to 2. So that should be the middle of the graph. Again, the 4 in front of the sign is amplitude. That means from 2, this graph is going to go as high as 6, and it's going to go as low as -2. So the maximum of my graph is here at 6. The minimum of my graph is at -2. And then I'll mark off pi over 2, pi, 3 pi over 2, and 2 pi. So my graph should end by here. Again, we're going to think about this in quadrants, one quadrant at a time. And this is sine. Sine, of course, starts in the middle. It goes to its maximum, back to the middle, then to its minimum, and then back to the middle. How long has it been since you've graphed a trig function? Probably a while. Hopefully it's a good review for us. All right, so quadrant by quadrant again. I'm going to start with quadrant 1, this piece of the graph here. When my theta is 0, my radius is 2. So up here at the theta of 0, I'm going to plot that point at a radius of 2. That's where I'm starting. And then by the time we get to pi over 2, my graph is at its maximum point of 6. So pi over 2, I'm going to go out to 6. Again, remembering that that darker circle signifies 5. Now we need to get that third point in there to kind of help us get the shape of the graph. This time, the convenient point is going to be at pi over 6 because it's a sine function. Sine of pi over 6 is 1/2. So r of pi over 6 is 2 plus 4 times 1/2, which would be 4. So on the pi over 6 spoke, there's our helpful point there at 4. And so our curve is going to look like this. All right, moving on to quadrant 2. We're going to pick up where we left off. By the time we get to pi, we're back at 2. So over here on where theta is pi, I'm going to put that point there at 2. Notice that this time my first and second quadrants, that's where the symmetry happens. And so it's going to be symmetrical up here too, quadrant 1 and quadrant 2. This point here has a radius of 4 on the pi over 6 spoke. We're going to have that same radius of 4 on the 5 pi over 6 spoke. So we're going to have that point right there. And so my curve, we're going to pick up where we left off, and it's going to continue around like this. All right, quadrant 3. This is where things get interesting. We're going to pick up where we left off. And notice when we finish quadrant 3, we're down here at -2. So when theta is 3 pi over 2, my radius is -2. So let's plot that point up here on our polar graph. Here's the spoke 3 pi over 2. If my radius is negative, that means it's going to go up. We're going to go in the opposite direction, and that point is going to be right here. So how do I get from this point to this point? If I get that helpful point at 7 pi over 6, r of 7 pi over 6, that's going to equal 2 plus 4 times -1/2. That equals 0. So we're going to go through the pole to get to this point. So this is still kind of hard to imagine what this is going to look like. So let's think about this. This section of the graph right here, this whole time when our graph down here is negative, my radii are negative, my angles are in quadrant 3. So if my angle is in quadrant 3, but my radius is negative, where does that point end up getting plotted? Well, it's going to end up in the opposite quadrant over here in quadrant 4. This first part where we're staying positive, this part is going to be in quadrant 3. So I'm going to connect from where we left off to the pole like this. Once I go through the pole, this part of the graph here is going to end up in quadrant 1. And it's going to go up to that point where we left off, or where we were supposed to end by the end of quadrant 3. Final quadrant, we're going to pick up where we left off. Notice these radii again are negative. My angles are in quadrant 4. If I have theta in quadrant 4, but my radius is negative, all of this is going to end up graphing in quadrant 2 because that's an opposite quadrant from quadrant 4. And then this part's going to finish out positive radii in quadrant 4. And of course, I'm going to end where we began at the same point, 2 pi, and the radius is 2. So for our negative radii down here, symmetrical there, quadrant 4 thetas, but it's negative radii, so they're graphing in quadrant 2, and then it goes positive. So now I end up back in quadrant 4 to finish out my graph. And so this is one of the limacon where we end up with this curve that has this inner loop. So hopefully we can see that that inner loop occurs because we have these radii values down here that are negative. In the next video, we're going to look at how to sketch those graphs of the rose curves.